There's this invisible force. It's pushing on you from every single direction right this second. And the crazy part, you don't even feel it. So today, we're going to make that force visible. We're diving deep into the fascinating world of gas pressure. Okay, I want you to try something. Picture a heavy bowling ball. Now imagine that bowling ball is sitting right on your thumbnail. Feels like a lot, right? Well, that's the amount of pressure the atmosphere is putting on every single square inch of your body, all the time. It's this huge invisible weight, and it's always there. So if that force is really that strong, a bowling ball on your thumbnail, why aren't we all just, squished? The answer to that question, well, that's the whole secret to understanding what pressure really is. Well, the thing is, we're basically living at the bottom of a giant ocean, an ocean of gas. And what we call pressure is really just trillions and trillions of tiny gas molecules constantly bombarding you from all sides. The reason it doesn't crush you is because your body is pushing back with the exact same amount of force. It's a perfect stalemate. But make no mistake, that force is real. If you mess with that balance, say by sucking all the air out of a giant metal tanker truck, the atmosphere will crush that thing flat, just like you'd step on an empty soda can. It's pretty incredible. Okay, so to really get a grip on this, we need to look at more than just the force. It's not that simple. We've got to dig into this crucial relationship between force, area, and of course, pressure. And here's the secret sauce, right here. It's a super simple formula. Pressure equals force divided by area. That's it. This little equation tells you everything you need to know. It shows us that pressure isn't just about how hard you push. It's about how concentrated that push is. So you can crank up the pressure in two ways. Either push harder, or, and this is the really cool part, shrink the area you're pushing. All right, let's put this to the test with a little brain teaser. Who do you think exerts more pressure? A massive 7-ton elephant or 120-pound figure skater gliding on ice? Now, your first instinct is probably to say the elephant, right? It's an elephant. But the answer might not be what you think. Okay, so let's look at the numbers. The elephant, its weight, its force, is a jaw-dropping 14,000 pounds. But, and this is a big but, that weight is spread out across 4 absolutely massive feet. Now look at the skater. She's only 120 pounds, but all of that force, every single ounce of it, is focused onto the razor-thin edge of 2 tiny skate blades. So what's the verdict? The figure skater. It's not even close. She's exerting about 30 pounds per square inch. That's what lets her literally slice through the ice. The elephant? Despite being way, way heavier, it's only putting down about 14 pounds per square inch, less than half. It's the perfect illustration of why concentration is everything. So at the end of the day, it all comes down to this. Pressure is just concentrated force. Think about it. A sharp knife cuts way better than a dull one, right? It's not because you're pushing any harder. It's because all that force is focused on a much, much tinier edge. And that right there is the secret of pressure in a nutshell. Okay, so we get what pressure is now. But how in the world do you measure something you can't even see? Well, it took a bit of genius to figure out how to make this invisible force visible. The classic invention for this is the barometer. Here's how it works. You take a long glass tube, sealed at one end. You fill it all the way up with mercury. Then you flip it upside down into a little dish that also has some mercury in it. Now what happens is the air pressure from the atmosphere pushes down on the mercury in the dish, and that pressure is what holds the column of mercury up inside the tube. So if the air pressure is high, the column goes up. If it's low, the column goes down. It's such a simple but absolutely brilliant way to actually see the weight of the air around us. But wait a minute, why mercury? It's pretty nasty stuff. Couldn't you just use water? Well, you could try, but since water is so much lighter, so much less dense, the air pressure would push a column of water more than 10 meters into the air. That's over 30 feet. You'd literally need a 3-story building just for your weather station. So yeah, mercury being over 13 times denser just makes the whole thing a lot more manageable. And because of these different ways of measuring, we've ended up with a bunch of different units for pressure. You've definitely seen some of these. You've got PSI, pounds per square inch, for your car tires. Meteorologists often talk about atmospheres, or ATM. The standard scientific unit is the Pascal. And in a doctor's office, they're still using millimeters of mercury, or mmHg. They all sound different, but they're just different ways of talking about the exact same thing. And this isn't just for scientists in a lab. You see this stuff everywhere. I mean, it's fundamental to our daily lives, from what's happening inside your own body to what's happening outside your window. For example, I'm sure you've had your blood pressure taken at the doctor's office. You know, that cuff they wrap around your arm? Well, the fancy name for that device is a sphygmomanometer. Yeah, it's a mouthful. All it's doing is using air pressure to gently squeeze your arm, and then it measures the pressure of the blood in your arteries as it lets the air out. So when the nurse tells you your reading is something like 120/80, what does that actually mean? Well, those are two different pressures. The top number, the systolic, is the peak pressure right when your heart beats and pushes blood out. You can think of it as the power stroke. The bottom number, the diastolic, is the pressure when your heart is resting in between beats. And check out the unit they use, millimeters of mercury. It's a direct callback to those original mercury barometers. Pretty cool, huh? Okay, so let's zoom out, way out, from the scale of our own bodies to the scale of the entire planet. Because on a global scale, pressure is literally the engine that drives all of our weather. It's simple, really. Air always wants to move from an area of high pressure to an area of low pressure. And that movement of air, we call that wind. This is basically weather forecasting 101. When you see a weather map with a big L on it, that's a low pressure system. Air is rising up, and as it goes up, it cools down and forms clouds. That usually means rain or storms. On the flip side, a big H means high pressure. That's when you get those beautiful, clear, sunny days. And all those curvy lines you see swirling around, those are called isobars. They just connect all the spots that have the exact same air pressure. It's like a contour map for the air, and it gives us this perfect picture of how this invisible force is shaping our world minute by minute. So when you think about it, from the blade of a figure skater to the beat of your own heart, all the way up to the clouds in the sky, this invisible force, gas pressure, is just constantly at work shaping everything around us. So here's the question I want to leave you with. Now that you can see it, now that you know what to look for, where else are you going to spot this incredible force in action?